Hey guys, what's happening? Back here with your day 2 notes, your second notes that you're going to be taking on limits. Today we're looking at limits at infinity, both limits that can equal infinity and limits as x goes to infinity or negative infinity. And we're going to take a look at solving limits algebraically by two different ways today, by factoring and by expanding. So, and once again, when you're done with this video, hit the submit button on the screen and submit a photo of your notes. You guys were able to figure that out really well last week. Just remember to do that again this week. Okay, so let's start taking a look at what happens when we do limits around vertical asymptotes. So here we have a graph. Let's call this blue line the line f of x. If you want to just take a second and pause the video and sketch that graph in with those three different vertical asymptotes, we're going to take a look at solving limits around these vertical asymptotes. Okay, so the first question that you might get asked in a scenario like this is, what is the limit as x goes to negative 3? Of f of x. So when we take a look at this question here, notice that this isn't a right-hand or a left-hand limit. This is simply asking what is the limit as x goes to negative 3. So we need to consider both pieces. So I'm going to annotate here with a red marker. So let's check the right-hand limit first. As we approach negative 3, an x value of negative 3, we can see that our y value keeps going higher and higher and higher, right? So in a sense, we know that the limit as x goes to negative 3 plus of f of x would be infinity. We know that's how vertical asymptotes work, right? It just keeps getting higher and higher and higher. Right at negative 3, the function's undefined. But as we approach from the right, we keep getting higher and higher and higher. But what if we looked at a left-handed limit? The left-handed limit here we can see that as we approach negative 3 from the left side, we keep getting more and more negative, right? So this is approaching negative infinity. So let's think about what we had in class today. When the right-hand limit and the left-hand limits are different, that means that the limit does not exist. So the only acceptable answer here is that this limit does not exist. Okay? But what about as we approach negative 1? Well, as we can see, we have another vertical asymptote at x equals positive 1 here. That negative 1 is on the y-axis. As we approach 1 from the right or the left, both sides are approaching negative infinity. Now, you have a couple of options here how you want to report this. We could say that this limit equals negative infinity. Because as we approach from the right, we're approaching negative infinity. As we approach 1 from the left, we're also approaching negative infinity. So we can say that that limit as x goes to 1 of f of x is negative infinity. Also acceptable is saying that this limit does not exist because of the vertical asymptote. So D and E would be an option there as well. I kind of like the answer of negative infinity, because it's kind of telling us a little bit more what's happening there. Similarly, the limit as x goes to 4 here, we can see both from the right and from the left of that vertical asymptote, our limit is approaching positive infinity, right? So we can say up here, the limit as x goes to 4 of f of x would be positive infinity, Or again, you could say it does not exist because it's a vertical asymptote. Okay. So that's how we deal with limits around vertical asymptotes, right? We could get DNE, we could get plus infinity, we could get minus infinity, negative infinity. Let's take a look at limits as x goes to infinity or limits as x goes to negative infinity. So these are our extremes. We learned about extremes in pre-calculus, right, and horizontal asymptotes. Well, limits as x goes to plus or minus infinity are our horizontal asymptotes. So I'll give you a second to pause here the video while you can sketch a quick copy of this graph in. Then I'm going to ask you a couple of questions about this graph. Okay, so the first question is this. What is the limit as x, by the way, I should label this graph, this blue line, we'll call it g of x this time. This is a graph of g of x. So the limit as x goes to infinity of g of x would be equal to what? Well, when we take a look at this, okay, what is going to infinity here? Well, we can see down here, it's the x that's going to infinity. So as x gets infinitely large, notice it's positive infinity, right? So we're looking for x values that are really, really large, so way out here. Well, we know that this dashed line is saying that we have a horizontal asymptote. G keeps getting closer and closer and closer to that y value, maybe without ever even hitting it, okay? But our limit then, we would say, as x goes to infinity of g, here would be positive 2. What then do you suppose would be the answer to this question? What is the limit as x goes to negative infinity of g of x? Well, again, as x gets infinitely negative, I'm looking at g going back this way, right, for really, really negative x's. And I can see, once again, it has a horizontal asymptote. It's flattening out there at -1, -2, -3, -4. Okay. So that's how we deal with extremes. Horizontal asymptotes show up in these limits as x goes to infinity and x goes to negative infinity. Now, just backing up just a hair, let me back up one slide. Take a look at this graph. If this line continued to go up and up and up forever, then we might say the limit as x goes to infinity would be infinity. Okay, or let's say the line actually went down forever, like a linear graph or something, then we could say the limit as x goes to infinity might be negative infinity or positive infinity. Only when we have a horizontal asymptote do those limits as x goes to infinity or negative infinity come out to a real number. Okay, let's talk about solving some of these limits algebraically. Okay, so what I want to do here is, how can we do this without a graph? Okay, that's the question. How can we do this without a graph? Because you're going to be asked some limit questions on the AP exam, and you may not have access to your graphing calculator or a graph of the function. So how do we do that? Well, let's take a look at this first question. This first question says the limit as x goes to 3 of negative 4x plus 5. So that's our function, negative 4x plus 5, and x is going to 3. Let's take a look at that on a graph and see what the answer is first off. Right, so we can do negative 4x. Oops, I need to do it in my y equals. So I'm going to do negative 4x plus 5. That's my graph. I'm going to delete this other line that I have in here. Okay. And I just want a normal window, so I'm going to do zoom 6 for a standard window. And here's my function. Okay. So I know, right, we should know that that was going to be a linear function anyways, just based on the fact that we know negative 4x plus 5 is a linear function. But again, the question is, What is the limit as x goes to 3? Well, let's see what's happening here at 3 on this graph. I'm going to go ahead and trace 3. And I see that on my function, it's right here at y equals -7. Well, again, if I'm approaching from the right or approaching from the left, both of these are approaching the same value of -7. Well, how could I get that without a graph? Well, it's very simple. I just plug in 3 for x. So one of the first things we can do to try and solve a limit is try plugging in 3 for x. If we get a defined answer, that's going to be our answer.
So I plug in 3 here. I get -4 times 3 plus 5, which gives me -12 plus 5, which equals -7.
Very simple, not very interesting. The likelihood of seeing a problem like that on the AP exam, pretty low, because it's pretty easy to just plug in and solve. But I want to take a look at question number 2 here, because this is much more interesting. Okay? So here I have the limit as x goes to -2 of this rational function, x squared minus 4 over x plus 2. So you might say, well, let's just plug in, see what happens.
I agree. Let's see what happens. What happens when we plug in -2? Well, on top, we're going to get -2 squared minus 4. On the bottom, we're going to get -2 plus 2.
That gives us, right, a negative squared is positive, right? So we get 4 minus 4, which is 0,
over -2 plus 2, which is 0. So plugging in
gives us 0 over 0. Well, 0 over 0 is undefined. But think back to your pre-calculus days. What happens, right? What happens when you have 0 over 0 coming up on a rational function? Well, this is telling you something very important.
This is telling you
that there was a hole in the graph. Now, when there's a hole in a graph, we know that limits can exist, right?
So if we think about a graph with a hole in it,
when I showed you a graph like that, the limit for sure existed, right? We practiced that today in class. Okay? So what we want to do now, when you plug in, if you get 0 over 0, just for notation's sake,
we want to go ahead and cross off that work,
because we know 0 over 0 is not the answer. Okay, so we can just cross it off. I want you to get in the habit of crossing that off, because what we can't have is false equivalency. We're eventually going to get this to equal a number, and we can't have this limit equaling 2 different things, because it can only equal one thing. Okay, well, let's take a look at this on a graph and see if we can figure out what's going on. So I'm going to go ahead and graph this function. I'll go back to my y equals. Again, to put in a fraction on your calculator, hit alpha, y equals, enter. And on top we had x squared minus 4. And on bottom we had x plus 2. Okay, let's take a look at this graph, see what it looks like. Interestingly enough, this graph looks very linear. Okay, but we're trying to figure out what's happening at -2. So again, let's trace -2. We can see that it says y equals blank. Anytime you see y equals blank, that means your function is undefined. So if you were graphing this in pre-calculus, you would have put a hole right here in your graph. The calculator can't really pick that up very well. Okay? But we can see here that when x equals -2, we're approaching the same from the right and from the left, right? We can see that the limit is certainly going to exist. It's not going to be a D&E limit. So let's try tracing numbers right around -2 and see what our y value is really close to, right? We might be able to approximate it here It looks like it's pretty close to maybe -4 or something, but let's try it. So I'm going to trace numbers close to -2. I'm going to try -1.9. And now I see -1.5, sorry, -1.9 is defined. I'm going to get -3.9. In fact, I'm going to test even closer. I'm going to do -1.999. I'm going to get really close to -2. Now, -1.999, this is like our right-hand limit because we're approaching from the right. And I see that my y value is -3.999. Well, this is a number really, really close to -4. So that's like my right-hand limit being -4. Let's check a left-hand limit by doing a number a little bit less or a little bit more negative from that. And once again, I see that my y value is -4.001. Again, really close to -4. So I can see graphically here that my answer should be -4.
I know that this answer actually equals -4.
But how could I do that without a calculator? Well, one of our methods algebraically for solving limits is to try factoring and canceling. So let's try that. Now what I notice here is x plus 2 doesn't factor. I mean, I could factor out a 1. The denominator here doesn't really factor, but the numerator does. The numerator is definitely a difference of squares.
So I know, rewriting this problem, I could solve this by doing, I can factor that top into x plus 2, x minus 2.
Because I know that x plus 2 times x minus 2 is the factored form of x squared minus 4. Now, when I do that, something really nice happens. What happens is I can cancel out
an x plus 2 on top and an x plus 2 on the bottom.
That's getting rid of the 0 that's being caused on top and the 0 that's being caused on the bottom, right? Plugging in -2 to x plus 2 will always make 0, and I'll always have a 0 in the denominator, which is a big problem. Once I cancel those out, now I can replug in my number.
And when I plug in -2, I get -2 minus 2, which equals -4. And that's my answer to this problem.
Okay, so we factored and we canceled to get out of that tricky 0 over 0 situation. Again, let's try it on the next one. Go ahead and plug in and see what happens. Well, I've got 2 squared, which is 4. 4 plus 3 times 2, 4 plus 6 is 10. 10 minus 10 is 0.
I'm getting a 0 on top.
On the bottom, 2 squared is 4. 4 minus 18 is, oops, sorry, that should be a plus. Four minus 18 is -14. -14 plus 14 is 0. By the way, if I would have left that as a -14, I would have got 0 over -28, and my answer would be 0. That's the answer. Okay? It's only when we have 0 over 0 that we're going to have this weird stuff going down.
So once again, get in the habit. Right away, let's cancel this out.
We know that that means it's a whole. So let's go ahead and see if this thing can factor and cancel. So when I look at the top, right, they're both quadratic, so they're both, I could use the RS method on either one. When I look at the top, I think of what two numbers multiply to make -10, but add to +3. Well, again, if they're multiplying to make a negative number, I know one must be plus and one must be minus. The bigger one's got to be plus. So I can see right away that this is going to be x plus 5 and x minus 2.
And again, when you rewrite this limit notation.
And they want to see that limit notation each time you're doing this.
So we're going to have x plus 5 and x minus 2.
And on bottom, two numbers that multiply to make positive 14, but add to negative 9. Right? If they're multiplying to be positive, but adding to be negative, they both have to be negative. That's going to be x minus 2 and x minus 7. Do we see anything that can cancel? Yep. We can cancel out those x minus 2s.
Right, those were the problem.
That x minus 2 was giving us the 0 on top and the 0 on bottom. Now all we have to do is plug in and solve. So when I plug in 2 into the top, 2 plus 5 is 7. So I get a numerator of 7. And when I plug 2 into the bottom, 2 minus 7 is negative 5. So I get my limit equals negative 7/5. And again, you can go ahead and graph that thing and check numbers really close to 2, and you'll see an answer that's very close to negative 7/5. All right, negative 1.4. Okay, last problem before we're done today. Let's look down at the very last problem. Here we see the limit as x goes to 0 of x plus 4 squared minus 16 over x. So again, what happens when we plug in 0? Well, we get 0 plus 4. 0 plus 4 is 4. 4 squared is 16. 16 minus 16 is 0 on top. And a 0 on the bottom. Again, that just means there's a hole. Don't worry about it. Just cross it off and just know we have to do something else. Now, we can't factor this one because it's already kind of in factored form. But another trick we can do is expansion. So we can expand this numerator, and hopefully we can get an x to cancel out an x that's on the bottom. So when I expand x plus 4 squared, right? Yeah, when I write this, I need to write my limit notation again. It gets kind of annoying, but it's what we have to do. X plus 4 squared literally means x plus 4 times x plus 4. Now, there's nothing I can cancel right here. Right? I can't cancel those x's because there's not an x in every term. But what I'm going to do is I'm going to FOIL this out. So here's what I'm going to get. I'm going to get x squared. I'm going to do my outer. X times 4 is 4x. I'm going to have another 4x, so that's going to be a total of 8x. And last, I'll get plus 16. But don't forget, I still have this minus 16. Once again, I can't cancel the x because not every term has an x. But hopefully you're seeing something that does cancel in the top. Notice how we have a plus 16 and a minus 16 up there? Those two are going to add to make 0. So I'm going to get limit x goes to 0. Right? These two right here add to make 0. So I'm going to get x squared plus 8x over x. Now this is nice because every term does have an x. Now I can factor out an x from the top and cancel it with the x on the bottom. So factoring out an x on top, I'm left with x plus 8. And now, since I have multiplication, I can cancel those two x's. After you do your cancellation, now go ahead and plug in 0 for x. Plugging in 0 here, 0 plus 8 equals 8. Go ahead and plug that original function into the calculator. I'm not going to do it now just for sake of time. Go ahead and plug this into your calculator and trace numbers right around 0, maybe 0.001 or negative 0.001, and you should see numbers very close to 8. All right, that's it for today. Again, have these notes, a picture of them submitted by Wednesday night at midnight, and I'll talk to you guys later. Bye.